In this paper, we present Neet, a method for reconstructing arbitrary surfaces from multi-view images. Our main idea is to represent the 3D surface using a level set of assigned distance function, coupled with a validity branch to estimate the probability of the surface existing at the query positions. We have developed a novel neural volume renderer that avoids rendering points with low validity and supports easy field-to-mesh conversion. Neet is able to reconstruct close surfaces from multi-view images. Reconstruct open surfaces from multi-view images. As well as reconstruct open surfaces from a single image.
Hello everyone, this is Xiaoxu Meng, a senior researcher from Tencent. Here I'm glad to present our work, Neet, Learning Neural Implicit Surfaces with Arbitrary Topologies from Multi-View Images. Our goal is to learn geometries with both open and closed surfaces from multi-view images, and export high-fidelity and normal consistent meshes from the neural representations. This provides a promising alternative for learning 3D shapes directly from 2D images without 3D data. 3D reconstruction from multi-view images is a fundamental problem in computer vision and computer graphics. Recent advances in neural implicit functions have brought impressive progress in achieving high-fidelity reconstruction of complex geometries. However, existing neural rendering methods represent surfaces as SDF, limiting their output to closed surfaces. These approaches are not applicable in reconstructing real-world objects with open boundaries, such as plants and garments. The recently proposed NDF, 3P SDF, and GFs introduce new implicit representations, supporting 3D geometry with arbitrary topologies. However, none of these methods are compatible with the current neural rendering frameworks. In our work, we fill this gap by presenting Neet, a neural rendering framework that supports reconstructing both closed and open surfaces from images and supports efficient field-to-mesh conversion. So the basic idea is to represent the surface as a level set of SDF with a validity branch for estimating the surface existence probability at the query positions. Here is a 2D example. With a given SDF, we could export a closed surface. In Neet, we also use a validity branch to estimate the validity of the SDF space. For instance, if we know the probability of the bottom line being valid is 0, we assign not a number to the low validity SDF. This helps us extract open surfaces instead of a closed surface using the margin cubes algorithm. We develop a neural volume rendering method to support learning neural implicit surfaces from the images. Given a sampled pixel on the input image, we project it to the 3D space to generate the sampled 3D points. Then we predict the sign distance, the validity probability, and the RGB value of the sampled points. In the training stage, the predictions are delivered to the Neet renderer to render images and masks, which are used for loss calculation. In the testing stage, we set SDF of the low validity points to none and extract open surfaces with the margin cubes algorithm. To introduce the detailed design of the Neet renderer, we start from introducing the difference between rendering watertight and open surfaces. The first difference is the rendering of back faces. Conventional SDF-based approaches do not consider the back faces, but this approach will result in empty renderings in the back cameras. To address this issue, we render each point with re-intersection. The second difference is the definition of inside and outside, which do not exist for non-watertight surfaces. We leverage the local surface normal to determine the sign of the distance. We expect that the rendering behaves the same when the ray crosses a surface from either direction. In the probability density function, we modify the SDF value by flipping its sign in the regions where the SDF values increases along the camera ray. Then we could derive the opacity from the probability density function. The surface opacity is a multiplication of the SDF opacity and the validity probability. In this way, we avoid rendering the surfaces that do not exist. We supervise the training of NeAT with 5 losses. Except for the commonly used RGB loss, mask loss, and icono loss, we additionally added 2 regularizations. The validity regularization accounts for the binary existence of the surfaces, while the sparsity regularization prevents redundant surface prediction for open structures. We validate Neet using 3 experiments. We first conduct multi-view reconstruction for real-world watertight objects. The results reconstructed with our method show comparable quality compared with the state-of-the-art. Second, we reconstruct open surfaces from multi-view images. We run this experiment on the multi-garment NeAT dataset and Deep Fashions 3D dataset. Neet generally provides lower numerical errors. Also, Neet is able to reconstruct high-fidelity details with consistent normals like the thin straps of the tops. Finally, we reconstruct an autoencoder, which takes a single image as input and provides validation on the challenging task of single-view reconstruction on open surfaces. The qualitative results show that our method can infer accurate 3D shapes from single-view images. We conduct 2 ablation experiments. The first ablation shows that the regularizations about validity helps on reducing noisy faces and the redundant surfaces in the output. The second ablation explores the reconstruction with different number of views. The reconstruction quality improves with the increase of views, but Neet can still reconstruct open surfaces even with sparse views. There are 2 limitations with the current method. The first limitation is that the empty space around the collar is mistakenly connected to the main body due to limited input views and occlusions. The second limitation is that Neet has difficulty in reconstructing very thin closed surfaces, like the umbrella stretches. To overcome these limitations, future work could involve introducing more advanced adaptive sampling and weighting mechanisms for reconstructing complex structures. Additionally, it could be promising to explore ways of handling in the wild images without camera parameters. Thanks for watching. Welcome to visit our website for more details.